So as we've already discussed, oxygen is carried through the blood on hemoglobin, which is a protein that has quaternary structure. It has 4 subunits, and each one has a heme group with iron in it that can bind an oxygen molecule. And when we say that hemoglobin is completely saturated with oxygen, we mean that the hemoglobin is carrying all of the oxygen molecules that it's capable of carrying. So here on the y-axis we have the percent saturation of hemoglobin with oxygen, and notice that it goes from 0 to 100%. So at 0% there's no oxygen on the hemoglobin at all, and at 100% up here every single hemoglobin molecule is carrying oxygen. And what this graph tells us is that the amount of saturation of hemoglobin with oxygen depends on the partial pressure of oxygen. So if there's no oxygen, if the partial pressure is 0, then we have 0% saturation, which completely makes sense. And then as we increase the partial pressure of oxygen around the blood, we increase the saturation of hemoglobin until we reach 100%. And it just so happens that where we get almost 100% saturation of hemoglobin is at a partial pressure of 100. And do you guys remember where the partial pressure of 100 is? That's typical of the blood in the alveoli. So blood in the alveoli is typically at 100% saturation. So as the blood passes through those capillaries and the partial pressure around it is 100 millimeters of mercury, the blood becomes, or the hemoglobin rather, becomes completely saturated with oxygen. And so we say that when we talk about the affinity of hemoglobin for oxygen, we mean that its ability to bind it. So if it has high affinity, it binds it tightly. If it has low affinity, it doesn't bind it tightly. And the affinity actually changes. And this is important because when we get around working cells, we want the hemoglobin to let go of the oxygen so that it can diffuse out of the blood and into the cells. But when the blood goes through the pulmonary capillaries, we want it to pick up the oxygen. So the affinity actually changes. Just one other landmark on here, remember the partial pressure of 40. This is typical of a resting cell. So remember when we looked at our drawing of the oxygen, of the blood circulating and exchanges with the tissues, remember we said that the venous blood returning to the heart in a person who's resting typically has a partial pressure of oxygen of 40 millimeters of mercury. And if we follow this up to the graph, up to here, and then draw a line across, you see that the percent saturation of the venous blood returning to the heart in a resting person is about 75%. That means that what we call deoxygenated blood returning to the heart from the systemic blood vessels is actually still about 75% saturated with oxygen. That means you have a tremendous reserve capacity because, for example, when you're exercising, the partial pressure of oxygen in your venous blood might go down even lower into this range here, so that the venous blood returning to your heart might be more like 35% saturated. And then, of course, as it moves through the pulmonary capillaries, it becomes completely saturated with oxygen again. So even when you're exercising, your arterial blood should always be close to 100% saturated with oxygen, but it might go quite low in your venous blood returning to your heart. Okay, so we said that the affinity of hemoglobin for oxygen needs to change as the blood moves through different parts of your circulatory system. So it needs a high affinity in your pulmonary capillaries, but as it's moving through tissues that have increased oxygen demand, the affinity has to go down. So we can draw a curve on here representing hemoglobin with lower affinity, and we simply we call this a right-shifted curve, the lower affinity curve. So this is, green curve is decreased affinity. And that means the shape of hemoglobin actually changes, because remember, hemoglobin's a protein, and it changes in such a way that it doesn't bind oxygen as tightly. And so what we can say is when we have oxyhemoglobin, which means oxygen is bound to hemoglobin, we have a tendency to drive this reaction in the direction that we let go, that the hemoglobin lets go of the oxygen. So what conditions of the blood would cause hemoglobin to change its shape and reduce its affinity for oxygen? Well, there's several. One of them is a decreased pH, so more acidic, or if there's an increased temperature of the blood, or if there's more CO2 in the blood. And all of these conditions here are typical of blood around a working muscle, for example. So if you think about when cells are metabolically active, they have acidic byproducts, they're making CO2, the temperature's warmer around working muscles, and all of these factors change the shape of hemoglobin so it lets go of the oxygen more easily. There's another factor that's important is this chemical called 2,3-DPG, or diphosphoglycerate. And this is a chemical that's associated with hypoxia, or low oxygen. So if you are anemic, for example, for a long period of time, or you're at high altitude, then your red blood cells will release 2,3-DPG, and this is an allosteric modulator of hemoglobin. So it binds to hemoglobin and changes the shape of it, and the hemoglobin will let go of the oxygen more readily. So these are factors that cause decreased affinity of hemoglobin for oxygen. And we can think of these as related to working cells, with a much higher oxygen demand. So you would expect that hemoglobin should let go of the oxygen. Well, what about increased affinity? So there are conditions that can change the shape of hemoglobin so it actually binds oxygen more tightly. And I'm going to draw my increased affinity curve in blue. Can't go above 100% here. So this is increased affinity, which is our left shift. And when we have increased affinity, we have a tendency for hemoglobin plus oxygen to form oxyhemoglobin. And so what causes increased affinity? Well, if you think about where you want increased affinity, that would be the blood that is moving past the alveoli, or moving past less active tissues. And so what we see is if we have basically the opposite conditions to decreased affinity, so higher pH, lower temperature, less CO2, and less 2,3-DPG. And these are factors that increase the affinity of hemoglobin for oxygen. And so this is typical of the blood in the pulmonary capillaries. I'm just going to abbreviate that. Pulmonary capillaries. So if we write out this whole reaction of, I'm going to write this in another color. If we have hemoglobin plus oxygen, this is a reversible reaction forming the oxyhemoglobin. So when we have a right shift of the curve, we have a tendency to move the reaction get a pointer, in this direction. And when we have a left shift, we have the tendency to move the reaction in this direction. Another factor that we need to talk about that causes an increased affinity of hemoglobin for oxygen is when you have a different type of hemoglobin. So if we look at our graph again, and we've got our partial pressure of oxygen in millimeters of mercury on our x-axis and our percent saturation of hemoglobin with oxygen on our y-axis, if we have an increased affinity, recall then we have this left shifted curve. And if you have a hard time remembering left and right shift, here's the way I learned it. I will say, okay, if I've got higher affinity, then for any particular partial pressure of oxygen, so let me pick 20 as an example, here's my normal curve. If I have higher affinity, I'm going to have a higher saturation of oxygen. So that means I have to be shifted to the left. And that's the way I remember it. So an example of a type of hemoglobin that could be different is when you have fetal hemoglobin. So here this blue curve is representing fetal hemoglobin, and the red curve is representing maternal hemoglobin. And so what this means is that a fetus is able to steal away the hemoglobin from the mother's blood, which is really important because they're sharing circulation, and if the hemoglobin didn't have a higher affinity for oxygen in the fetus, then there wouldn't be much of a tendency for oxygen to diffuse into the fetal blood. And the proteins are different, so there's different genes expressed at different times of development, and in a fetus they produce different subunits of the hemoglobin than adults do. And when babies are born, one of the reasons they have so much jaundice is that they're breaking down the fetal hemoglobin, and of course the bilirubin pigments, which are yellow, are the byproduct of the breakdown of this hemoglobin.